Hello everyone, welcome to OHM Institute. I am Surendra Reddy, faculty for electrical machines at OHM Institute, Hyderabad. So this lecture I am going to cover 1 mark questions. In the next lecture, I'll discuss about 2 marks questions. Okay, and here we go. So this is the first question we are going to solve. This is the question in GATE 2011 paper. Okay, so read the problem. A single phase air core transformer fed from a rated sinusoidal supply is operating at no load. The steady state magnetizing current drawn by the transformer from the supply will have the waveform, and 4 waveforms were given. Okay, you can see these are the 4 waveforms given, 4 options. What is going to be the correct answer is the question. First of all, if you read the problem carefully, you can understand it was very clearly mentioned air cored transformer. Yes. If air is the core medium, definitely there is no discussion about magnetic saturation. Okay. We know in air medium, magnetic saturation will not be available. No saturation. If there is no saturation, can I say magnetization curve will be completely linear in nature? That means if you take magnetizing current on x-axis and flux on y-axis, definitely this is going to be a continuous linear line. Whereas if you consider a practical magnetic core, definitely you will use a ferromagnetic material. Therefore, saturation will definitely be there. If a saturation effect is considered, after knee point, you will find flux is going to reach saturation. But right now, air is the core medium for the transformer. That's why there is no saturation effect. When there is no saturation effect, flux and magnetizing current both are going to be sinusoidal. Now, what is the question? The question is about at steady state, what is the shape of the magnetizing current? That is the question. As I mentioned, flux and magnetizing current both are proportional to each other. That means if a flux has to be sinusoidal, magnetizing current is also going to be sinusoidal. Okay, so from this I can write flux is directly proportional to magnetizing current. Okay, so in order to create a sinusoidal flux, okay, the magnetizing current must also be a sinusoidal current only. Therefore, answer is going to be option C. Whereas if you consider a practical magnetic core, definitely saturation effect will be there. Therefore, you will get a curve like this. And due to that magnetic saturation, to produce a sinusoidal flux, a non-sinusoidal magnetizing current is required. And the shape of that non-sinusoidal magnetizing current would be a peaky nature waveform. If you have covered a harmonic analysis in transformers course, you might have studied about that point. Okay, so in a practical core, flux and magnetizing current cannot be sinusoidal at the same time because of saturation. But in the given question, air is the medium used where saturation is neglected. Therefore, flux and magnetizing current will be proportional to each other. Therefore, in order to create a sinusoidal flux, we need sinusoidal magnetizing current. Therefore, the answer is going to be option C. Okay, easy question. All right, let's move to the next problem. This is a question from GATE 2013 paper. A single phase transformer has no load loss of 64 watt as obtained from open circuit test. When a short circuit test is performed on it with 90% of rated current on its LV and HV windings, the measured loss is 81 watt. The transformer has maximum efficiency when operated at how much of the rated current? That is the question. So if we understand the problem carefully, it was very clearly mentioned no load loss of 64 watt. We all know that during no load condition, whatever the active power drawn by the transformer, that is definitely going to be iron loss. Okay, so therefore iron loss of the transformer is equal to 64 watt. This is what is obtained from OC test. Yes, OC test is used to determine constant losses of transformer, also known as iron loss of transformer. And the next one is short circuit test information is also given. See that short circuit test is performed on this transformer, but with 90% of rated current. It is not 100% of rated current. When current is 90%, then The measured loss is 81 watt. First of all, short circuit test will measure which loss? Copper losses. That means this 81 watt is definitely copper loss, but that is the copper loss measured at 90% of rated current only. But we need what will be the copper loss at 100% of rated current. Okay, so given at 90% current, copper loss is equal to 81 watt. But I wanted to know at 100% current, what will be the copper loss? This is the question I wanted to know. Yes, whatever the copper loss you measure at 100% of rated current, that is what we call it as a full load copper loss. If I know full load copper loss, then only I can find out efficiency or condition for maximum efficiency. Okay, so what is the relation between copper loss and current? Yes, we all know that copper loss is always proportional to square of the current. Okay, therefore I can write yes, I can write copper loss is proportional to square of the current. So copper loss in the first case means given data. Copper loss in the second case is required data, is equal to current in the first case divided by current in the second case whole square. It is direct proportionality. So first case, that is the given data, what is the amount of copper loss? 81 watt. But I wanted to know copper loss in the second case, that is at 100% current. So in the first case, current is 90% only. 90% means 0.9 times of rated current, divided by second case 100% current. 100% current means indirectly rated current whole square. Now you can understand rated current will cancel, 0.9 square will become 0.81. So you can find out copper loss in the second case. So that will be equal to 81 divided by 0.81. Can I say 100 watt? Now this is the copper loss at full load. Now once you know copper loss at full load condition, we can find out condition for maximum efficiency. Yes, what is the condition for maximum efficiency? We know at maximum efficiency, the load X is equal to square root of iron loss divided by full load copper loss, right? What is iron loss? That is already measured using OC test. So if I go back to the problem, all right, yes, OC test has 64 watt, that is iron loss, and the second one is full load copper loss. Therefore 64 watt divided by, we got full load copper loss 100 watt. Therefore if you solve it, you will get 0.8, X equal to 0.8. That means indirectly maximum efficiency can be obtained at 80% load. Okay, therefore maximum efficiency can be obtained at 80% load, So 80% load means out of the given options, the correct answer will be option C. 80% of the rated current, all right or not? Okay, so very simple question. So you should not confuse. Suppose if you assume this 81 watt is directly full load copper loss, then you will get a wrong answer, and that wrong answer will be definitely available in options. Okay, be very clear. When short circuit test data was given, the first thing we need to do is that compare test current with rated current. Here test current is only 90%. Rated current means 100%. Therefore, to calculate rated copper loss, I need to use 100% current. Based on that, I got 100 watt, which is the full load copper loss. All right, fine. So let's move to the next question. This is a question from GATE 2014. Read the problem. A single phase 50 kVA 1000 by 100 volt 2 winding transformer is connected as an auto transformer as shown in the below figure. The kVA rating of the auto transformer is how much? Very straightforward question. You see that actually we have a 2 winding transformer, and that 2 winding transformer has a power rating of 50 kVA. That is now converted into auto transformer, and the diagram was very clear. Input voltage was 1000, output voltage 1000 plus 100, 1100 volt. Therefore, what is voltage ratio K in auto transformer? Yes, we all know that in auto transformer, voltage ratio K is always equal to low voltage value by high voltage value of auto transformer. No matter what, no matter whether it is a step up auto transformer or step down auto transformer, ratio K is always defined as LV by HV of auto transformer. And here LV for auto transformer, low voltage is 1000, high voltage is 1100. That means K ratio is equal to 10 by 11. And once we know the value of K, then what is the volt ampere rating of auto transformer? Yes, volt ampere rating of auto transformer is always equal to 1 by 1 minus K times of volt ampere rating of 2 winding transformer. Okay, and if I substitute the data, 1 by 1 minus K value 10 by 11 into what is a 2 winding transformer KVA rating? 50. Therefore, if you solve this problem, you will get what is the VA rating of auto transformer. Okay, so if I solve this ratio, 11 times of 50, isn't it? So it will be 550 kVA. So this is the volt ampere rating of auto transformer. Okay, very simple and straightforward question. All right. So let's move to the next problem. This is a question in GATE 2014 again. Read the problem. Assuming an ideal transformer, the Thevenin equivalent voltage and impedance as seen from the terminals of as seen from the terminals X and Y for the circuit shown below are what? Okay, a very simple question. You see that you can look at the turns ratio given for this transformer. The turns ratio is 1:2. Primary side we have a voltage source. This is indirectly the voltage source. Magnitude of the voltage source is sine omega t, and the series impedance is 1 ohm. Okay, but I wanted to know what is the Thevenin voltage and resistance or impedance between terminals X and Y. But terminals X and Y are on the secondary side of the transformer. So simple thing you need to do is that transfer primary side parameters to secondary side. That's all. And according to turns ratio, if I transfer primary voltage to secondary side, 1 sine omega t, if it goes to the secondary side, it will become 2 sine omega t. Okay, therefore, voltage Thevenin between X and Y will be simply equal to 2 sine omega t. Okay, you see 2 sine omega t, 2 sine omega t. That means B and C are already ruled out. And the other thing you need to do is that transfer the impedance also. Let's say this is the impedance on the primary side. Let us say Z1, and we know if this Z1 transferred to secondary side, its value will become Z1 dash, right? And what is the formula? Yes, a simple shortcut is if you are transferring to the secondary side, the impedance value will be equal to secondary by primary turns whole square into original value. Or if you transfer the impedance to the primary side, simple shortcut is primary by secondary whole square into original value. That's it. If I am going to secondary side, multiplication factor is secondary by primary whole square. If I move to primary side, multiplication factor is primary by secondary whole square. Currently, I need to move this impedance to secondary side. Therefore, the answer is secondary by primary whole square. What is secondary by primary? 2 by 1 whole square, that will become 4. 4 into 1 ohm. This would be the correct answer. Okay, if you want to solve, you can do that. So I can write Z1 dash is equal to, as I am moving to secondary side, secondary by primary whole square times of its original value. So what is secondary by primary? 2 by 1 whole square times of Z1 is equal to 1. Therefore, the answer is 4 ohm. Okay, so that means what is the correct option here? Yes, Thevenin voltage will become 2 sine omega t and Thevenin impedance will become 4 ohm. 4 ohm. Okay, option A is the correct answer. Okay, simple question again. All right, let's move to the next question. This is a question again in GATE 2014 paper, 1 mark question. Yes, read the problem. For a specified input voltage and frequency, if the equivalent radius of the core of a transformer is reduced by half, the factor by which the number of turns in the primary should change to maintain the same no load current is what? This is the question given. Let us understand some important information given in the problem. For a specified input voltage and frequency, that means we are keeping voltage and frequency constant. One voltage and frequency is specified and they remains constant. Equivalent radius of the core is reduced by half. See, equivalent radius of the core is reduced by half. That means some change in physical dimensions of the magnetic core. Now, by how much factor the number of primary turns should change to maintain the same no load current? This is the condition. We wanted to maintain same no load current. In that case, what should be the change in number of turns? Okay. Now you see that, assume we have a magnetic core which is like a circular cross section. Imagine this is how the core looks like. Okay, imagine. Now this is what we call it as a cross sectional area of the core, and as it is like a circle, imagine the radius is equal to r. As they mentioned about radius, that's why I am taking a circular cross section. Okay. Now, what will be the area of cross section of this core? If I ask you, area of cross section is equal to pi r square. Am I right? Because it is like a circle. Okay. This is the cross sectional area I am talking about. Okay. Now, what happens if radius becomes half? If radius becomes half, can I say area will become 1 by 4 times? Because area is proportional to r square. If radius becomes half, area will become 1 by 4 times of the old area. This is the modification happened. If area is divided by 4, how much should be the change in number of turns so that we can maintain no load current constant? That is the question. First of all, we know no load current in a transformer will have two current components, right? No load current I0 is a combination of loss component current IW and magnetizing current I mu. So if you wanted to maintain a no load current constant, indirectly we have to maintain magnetizing current constant and also loss component current constant. If these two are constant values, definitely I0 is going to be constant. Suppose any change happened in any one of the parameter, definitely I0 is going to change. So let us talk about this magnetizing current first. Yes, magnetizing current is an active component or reactive component? Yes, magnetizing current is a reactive component and it is shown by a magnetizing reactance, okay, in shunt with equivalent circuit. So if you go through equivalent circuit of transformer, you might understood that there is a shunt reactance that will show magnetizing current. Yes, magnetizing current is equal to voltage divided by magnetizing reactance. And what is the formula for reactance? We know reactance is equal to 2 pi f into L, where L is the inductance of the coil. So if I use that here, V divided by 2 pi f into L. Already in the question very clearly mentioned, voltage is constant, frequency is constant. That means magnetizing current is inversely proportional to inductance of the coil. And what is the formula for inductance? Inductance of the coil is equal to number of turns square divided by reluctance. And remember guys, we wanted to keep magnetizing current constant. If I wanted to maintain magnetizing current constant, inductance must be constant, right? In order to make inductance constant value, if you wanted to maintain inductance constant, what should be the relation between N square and reluctance? Direct proportionality. Yes. Therefore, number of turns square should be proportional to reluctance of the magnetic core. What is the formula for reluctance? We know reluctance is equal to length of the core by mu into cross-sectional area. This is the formula for reluctance. Now see here, already what happens to area we discussed. Area is becoming equal to 1 by 4 times of the previous value. So let's go back. Yes, if area is divided by 4 times, okay, then number of turns square will be multiplied by 4 times. No other parameter was changing. Length is constant, mu is constant, only difference is area is divided by 4. If area is divided by 4, can I say n square is multiplied by 4? N square multiplied by 4 means n must be multiplied by 2. Okay. So therefore, I can write n square is multiplied by 4. That implies n is multiplied by 2. So if n is multiplied by 2, n square is multiplied by 4, which is satisfying this relation. That means L is a constant value. If L is a constant value, I mu is also going to be constant. So I mu will be constant if number of turns are doubled in this particular case. But our aim is to maintain only I mu constant or I naught constant. Yes, the aim is to maintain I naught constant. But I naught has one more parameter known as loss component parameter, IW. Yes, we all know that loss component current will depend upon iron losses in the transformer. Yes or not? Because that is iron loss component. This is a little lengthy question. Let's try to focus more. It's a microscopic level discussion. Okay. Yes. What is the formula for iron loss in transformer? Iron loss is always equal to voltage multiplied by IW. Our aim is to maintain IW constant. That is equal to iron loss by voltage. Can I say IW will be constant only when iron loss is constant? Because in the question already voltage is constant. I hope you are following, right? Voltage is already constant in the question. Therefore, iron loss is only IW is only proportional to iron loss. So if iron loss is constant value, then only IW will be constant value. If IW is constant, then only no load current I naught will be constant according to the question. But iron losses are again two types. What are the two types of iron losses we have? Hysteresis loss and eddy current loss. Okay. Right. So iron losses are two types. We have a hysteresis loss and eddy current loss. So if you wanted to maintain iron loss constant, indirectly I have to maintain hysteresis loss constant, eddy current loss constant. What is the formula for hysteresis loss? Hysteresis loss is always equal to eta into Bm square into frequency into volume of the magnetic core. Actually, it will be Bm power 1.6 and you can approximately take it as Bm square. Yes or not? And here volume is nothing but, I will rewrite this formula, Bm square into F into what is volume of the magnetic core? Area multiplied by length of the core. Here, what are the fixed values? Our aim is to maintain hysteresis loss constant. Eta is always a constant value because there was no change in the medium of the material. Length of the core was not changing. Frequency was not changing. What is the only thing changing? Area is changing. Therefore, what is the relation between Bm square and area? I can write Bm square is inversely proportional to area of the core. And what happened to area? Area is divided by 4. We discussed that already. Area is divided by 4 means Bm square is multiplied by 4. Bm square is multiplied by 4 only when Bm is multiplied by 2. That means indirectly, the new Bm must be 2 times of the old Bm value. Okay. New Bm is 2 times of the old Bm value. If Bm multiplied by 2, then only area is divided by 4. Alright. And Bm you can find out from voltage equation of the transformer. What is voltage equation of the transformer? Yes. EMF equation is equal to 4.44 into Bm into cross-sectional area into frequency into number of turns. And in the given question, voltage is a constant value, frequency is a constant value, yes or not? And what is the relation now? Bm is proportional to 1 by area into number of turns. From this, number of turns is proportional to 1 by Bm into area. Already we discussed area is divided by 4 and Bm is multiplied by 2. Bm multiplied by 2, area divided by 4, that means the number of turns will be multiplied by 2. Therefore, n is multiplied by 2. Is it the same conclusion we have drawn from magnetizing current also? Yes. In order to keep magnetizing current constant, there also we understood that number of turns must be multiplied by 2. Even in order to maintain hysteresis loss constant, we have to multiply number of turns by 2. But we have one more loss, guys. That is eddy current loss. What is see, our final aim is no load current should be constant. No load current will be constant only when IW is constant, I mu is constant. To keep I mu constant, n must be multiplied by 2 times. That is the conclusion. Next point, to keep IW constant, IW is a loss component current. Loss component current will be constant if iron loss is constant. Again, iron losses are 2 types, hysteresis loss, eddy current loss. To keep hysteresis loss constant, n must be multiplied by 2. That is the conclusion we have. Now let's talk about eddy current loss. In order to keep eddy current loss constant, how many times n must be multiplied? That is the discussion. Yes. What is the formula for eddy current loss? Eddy current loss is equal to K times of Bm square into frequency square into T square into volume of the magnetic core. I hope you know T is nothing but lamination thickness. What are the constant values in the question? Yes, in order to maintain I naught constant, I have to maintain eddy current loss constant. Frequency is already constant in the given question. Lamination thickness no change, that's why it is constant. K is a constant value because there is no information that medium of the core is changing. Therefore, you can make a conclusion here, Bm square is inversely proportional to volume. Volume is again area into, I will rewrite. Volume is again area into length of the core. We know length of the core is constant, only area was changing. That means Bm is inversely proportional to area. And what is our observation? Area is divided by 4 times. Area will be divided by 4 only when Bm square, that means Bm square is multiplied by 4. Bm square multiplied by 4 means Bm multiplied by 2. Okay, so therefore I can write Bm multiplied by 2. Multiplied by 2. Is it the same conclusion we had even from hysteresis loss also? Even from hysteresis loss also, the conclusion is Bm is multiplied by 2. If Bm has to be multiplied by 2, according to this relation, number of turns must be multiplied by 2. Therefore, I need not to solve it again. I can directly write, therefore, n must be multiplied by 2. Therefore, 3 discussions I took right now. One is magnetizing current. In order to keep magnetizing, I will go back. Yes, if you properly look at the question, the only thing that was happened is radius of the core is reduced to half. When radius was reduced to half, radius was reduced to half, area is divided by 4. But our aim is find the new number of turns. You need to calculate what should be the change in number of turns so that you have to keep no load current constant. Okay. So what is the first observation? Magnetizing current. Yes, magnetizing current will be constant only when number of turns are multiplied by 2. This is the first conclusion. Next, hysteresis loss will be constant only when number of turns are multiplied by 2. That is the second conclusion. Even eddy current loss is also constant only when number of turns are multiplied by 2. So in all the cases, it was satisfied that number of turns must be multiplied by 2, then only magnetizing current will be constant. Iron loss current component also constant. That means overall no load current will be constant. Therefore, the answer for this question is number of turns must be doubled, multiplied by 2. Then only no load current remains constant. Okay. It's quite a difficult model because we are analyzing 3 important factors. Okay. Right. Okay, so we have the next question. This is from GATE 2015 question paper. Again, it is a single 1 mark question, but a slightly a difficult model. Rather than transformers, I must say this is a coupled magnetic circuit question. So you will study generally in electrical circuits subject, magnetic coupled circuits. However, we can answer even in transformer subject as well. Okay, so just read the problem. The self-inductance of the primary winding of a single-phase 50 Hz transformer is 800 millihenries, and that of the secondary winding is 600 millihenries. The mutual inductance between these two windings is 480 millihenries. The secondary winding of this transformer is short-circuited, and the primary winding is connected to 50 Hz source. Current flowing in both windings, that is very clear. In this condition, what is the effective inductance seen by the source? Okay, first of all, a transformer will have two windings, right? Let's say this is a primary winding, and here we have the secondary winding. In the given question, secondary winding is short circuited, primary winding is connected to a voltage source, and between these two windings there is always mutual coupling. Am I right? Assume that mutual inductance is equal to M. Okay, and polarities are very important because we wanted to solve this question using magnetic coupled circuits manner. We know in a transformer, primary side, if current is entering the dot, secondary side current will always leave the dot, because a transformer is a negative magnetic coupling circuit. So primary side current entering the dot, secondary side current is leaving the dot. Assume primary winding has an inductance L1, self-inductance L1, secondary side winding has a self-inductance L2. Between the two we have mutual inductance M. And in the given question, what is L1 value? Yes, primary winding has a self-inductance 800 millihenries. Secondary winding has a self-inductance 600 millihenries, that is L2. And the mutual inductance between the two, M value is 480 millihenries. But I wanted to know what is the effective inductance seen by the source. This is the supply source. Therefore, what you do is that write KVL equations here. Okay. See, primary side current entering the dot, secondary side current is leaving the dot. Therefore, it is a negative magnetic coupling circuit. So, if I write the KVL equation, primary side we have a source voltage, right? Therefore, the supply voltage source is equal to primary side self inductance is there, L1 into di1 by dt. We know voltage according to Faraday's law, L di by dt. At the same time, mutual inductance is also there, but you have to write minus M into di2 by dt. See, mutual inductance means it is the voltage induced in primary winding due to the current passing through secondary winding. That is what mutual means. Okay. What is the definition for self EMF and mutual EMF? Self EMF means it is the voltage induced in that winding due to the current passing through the same winding. But mutual EMF means it is the voltage induced in that winding due to the current passing through other winding, which is mutually coupled to it. Okay. But why I am using minus sign? Because of negative magnetic coupling. Okay. Yes, therefore, supply voltage is equal to, what is L1 given? 800 millihenries di1 by dt. M value is given as 480 di2 by dt, right? Keep it as equation number 1. This is the KVL equation on source side. Let me check the values. Yes, primary inductance 800, mutual inductance 485. But if you look at the secondary side, as the secondary winding is short circuited, what is the voltage across the short circuit? 0. Therefore, let us write down the KVL equation on the secondary side. Secondary side voltage is equal to 0 because of short circuit is equal to, yes, a secondary winding has a self inductance, that is L2 into di2 by dt, same inductance, same current. But mutual inductance is due to the other winding, minus M into di1 by dt. Okay, this is the current passing through first winding, but voltage is induced in second winding. Here, this is the current passing through second winding, but voltage is induced in first winding. Okay, so 0 is equal to, what is L2 given? 600 millihenries into di2 by dt minus 480 millihenries into di1 by dt. This is equation number 2. Okay. Now what you do is that just use separate di2 by dt from this second equation. Okay. So if I take this product to the left side, 480 into di1 by dt is equal to 600 into di2 by dt. Separate di2 by dt. That is my point. Yes. If I separate di2 by dt, di2 by dt is equal to, take 600 to the left side, 480 by 600 times of di1 by dt. Can I substitute this di2 by dt in the first equation now? In the first equation already we have di2 by dt. Substitute this value. Okay. Then let us write what happens to source voltage Vs. Okay. I will go to the next page. Now source voltage Vs is equal to 800 times di1 by dt minus 480 into, we have di2 by dt, but what is di2 by dt from the last equation? 480 by 600 times of di1 by dt. So 480 by 600 times of di1 by dt. Now you can take di1 by dt common. So source voltage is equal to 800 minus 480 square by 600 into di1 by dt. So then what is this coefficient? If I solve it, 800 minus 480 square divided by 600. So I am getting 416 di1 by dt. Is it looking like effective inductance into di1 by dt? This is the source voltage. So finally source voltage looks like an equivalent inductance into di1 by dt. What is the value of that equivalent inductance? 416. So rather than transformers question, I must say this is a coupled circuit question. Okay, the effective inductance of the primary winding will be equal to 416. That is the answer. Okay, so the answer is option A, 416. So very simple thing I did, I just write the KVL equation. Primary winding has two voltages. One is due to self inductance, another one is due to mutual inductance. L1 into di1 by dt, that is self EMF, minus m into di2 by dt. Always remember, mutual EMF is not due to the same winding current, it is due to the other winding current. But why we wrote minus sign there? Because of negative magnetic coupling. Primary side current entering the dot, secondary side current leaving the dot. Okay. And finally I wrote the entire equation in terms of supply voltage, that is effective inductance into di1 by dt, and we got the answer 460. Okay, right. All right, let's move to the next question. This is from GATE 2016 question paper, 1 mark question. Read the problem. If an ideal transformer has inductive load element at port 2 as shown in the below figure, the equivalent inductance at port 1 is how much? Very simple. We have an inductance which is on the secondary side of the transformer. Now what is the effective inductance from primary side of the transformer? That means what you need to do is that just transfer this L value to the primary side. What is the turns ratio of the transformer given? It is n:1 ratio transformer. I told you already, yes, when you are transferring to primary side, the answer will be primary by secondary whole square. Therefore secondary side inductance is L. When it is transferred to primary side, assume it is L dash. Therefore L dash is equal to, we are moving to primary side, so primary by secondary number of turns whole square into the original value L. What is n1 by n2 according to the given question? N by 1. So the answer is n by 1 whole square into L. Therefore L dash is equal to n square times of L. That is the answer. Direct question. So it is n square into L. Actually this is option B. Option B, n square into L. That is the answer. Okay. All right. So we have the next question. This is from GATE 2018 question paper. Read the problem. A transformer with toroidal magnetic core of permeability mu is shown in the below figure. assuming uniform flux density across the circular core cross section of radius small r, which is less than the mean radius capital R. You can see from the diagram, small r is the radius of the cross section, capital R is the radius of the entire magnetic core. And neglecting any leakage flux, the best estimate for the mean radius capital R is, see, ultimately we have to find out a formula for this capital R with the available parameters. Okay, you can see here supply voltage was there and current was there. This is radius of the cross section, and you can see all the formulas are in terms of mu, voltage, small r, number of turns in primary, omega is the frequency, ns number of turns in secondary. I need ultimately what is the answer for that capital R. Okay, and how to proceed with this? Okay, very simple. You see that as a supply voltage was given, you see voltage is equal to V cos omega t. That means, can I say it looks like Vm cos omega t? That means this V is nothing but maximum voltage. First of all, what is primary voltage formula in transformer? Voltage is always, especially primary voltage, is equal to 4.44 into phi m into frequency into number of turns. This is actually the formula. But if you look at all the options, see, you can see there is a term involved in every option, that is V. V is involved everywhere. But here V is RMS value of the supply voltage or maximum value of the supply voltage, maximum value only, right? But this is RMS value of the voltage. If you know RMS value of a sinusoidal function, then what is the maximum value? You have to multiply with root 2. Therefore, maximum voltage is always equal to root 2 times of RMS voltage. So if I multiply root 2 into what is RMS voltage, 4.44 into maximum flux into frequency into number of turns. What is root 2 into 4.44 into root 2? Isn't it 6.27, or leave it like that? Root 2 into 4.44 into maximum or else a maximum flux into frequency into number of turns. Now you see that there is a term frequency here, but in all options we have frequency or omega is there. Yes, in all options omega is there. That means you have to replace frequency f in terms of omega. What is the relation? Omega is equal to 2 pi f. Therefore f will become omega by 2 pi. So I can continue. So root 2 into 4.44 into phi m, what is the frequency? Omega by 2 pi into number of turns. Now you see root 2 4.44 by 2 pi, then what is the answer? Yes, it is equal to 1. So these two will cancel each other. Therefore, maximum voltage is equal to simply phi m omega into number of turns. Okay. Now let us replace this phi m. What is the formula for flux? We know flux is always equal to mmf divided by reluctance. But in the equation we have maximum flux or just flux? Maximum flux. Therefore, I can write flux is equal to, what is the formula for mmf again? Number of turns into current divided by reluctance. Then maximum flux will be equal to maximum current. You will get maximum current, therefore you will get maximum flux. Right or not? And replace this maximum flux in the previous equation now. Okay. If I replace that maximum flux here, so Vmax is equal to, therefore Vmax is equal to phi max, number of turns into maximum current divided by reluctance into omega into number of turns. I think we are almost there. But I need to replace this reluctance also, because no option is having reluctance term. We have a formula for reluctance. Keep it like this. We will come back to this formula again. Let's go and find out reluctance. What is the formula for reluctance? Reluctance is always equal to length of the core by mu into cross-sectional area. What is the length of the core? It's a toroidal magnetic core, guys. I will go back. It's a toroidal magnetic core. Can I say length of the core is nothing but indirectly length of this circle? what is the length of this circle? Is it nothing but a perimeter of the circle with radius capital R? If radius is capital R, what is the perimeter is equal to 2 pi R. Therefore, length of the core is nothing but 2 pi R. So, length of the core is equal to 2 pi into capital R divided by mu into cross-sectional area. It's a circular cross-section. Therefore, can I write pi R square? Remember guys, this small r is cross-sectional area radius. Capital R is mean radius. Now what happens here? Pi cancelled. Therefore, reluctance is equal to 2 into capital R by mu into small r square. This is reluctance of the magnetic core. Now substitute this reluctance in the previous formula that we developed. What is the previous formula? V max is equal to n into Im by reluctance into omega n, and I got reluctance formula. Okay. Yes. Now see, V max is equal to n into Im divided by reluctance into omega n. Now what is reluctance? If I substitute this, V max is equal to n into Im divided by reluctance means you need to substitute this 2r, that mu r square will go to the numerator into omega n. Yes, now I got this capital R value. See, what is the final answer I need to find? I need to find a formula for this capital R just to separate this capital R now. Yes, I am almost there, right? Capital R we need to separate. So if I separate capital R is equal to, yes, numerator will have number of turns. See, number of turns into number of turns. Can I say number of turns square? Yes, numerator has number of turns square, and omega is there, mu is there, r square is there, I max is there, Im means I max, divided by 2 is there, and V max is there. And in the given question, what is I max, guys? Let's go back. Yes, look at this current expression. If you look at this current expression, is it looking like Im sin omega t? Therefore, that I is nothing but I max. Even in V also, V max is nothing but V. Okay, therefore, yes. So Im is I, Vm is V. So number of turns in primary, don't forget that number of turns in primary winding square, omega, mu, r square, Im is I, Vm is nothing but V. This is capital R formula. Finally, identify which option is having all these informations. You see, number of turns on numerator with square, current is on numerator, voltage is on denominator. Let's go back to the options. Okay, if I go back to the options, let me erase all these things. Current is in numerator, voltage is in denominator, right? According to our equation. Current is in numerator, that means this option is wrong. And this option is also wrong. Yes, here current is in numerator, voltage is in denominator. Current in numerator, voltage is in denominator. But this is the correct option. Why? Because 2 is there in the denominator, right? And the square of the turns, omega, mu, current, r square, 2v. So option D satisfied. Okay. There are multiple ways to answer this question. I answered this question using voltage equation. You can also answer this question from flux density point of view or flux point of view, magnetizing current point of view. Various procedures are there. I just used voltage equation. See, thing is that first write voltage equation, try to get every parameter according to the options. All right. So whatever parameters you have in the options, they should be there. And I found option D is the correct answer. Okay, right. Okay, so let's move to the next question. This is in GATE 2018 question paper. A single phase 100 kVA, 1000 volt by 100 volt, 50 hertz has series impedance drop of 5% at full load. Of this, 3% is due to resistance. Percentage regulation of this transformer at full load with 0.8 lagging power factor is how much? Very simple question. Impedance drop was given, that is indirectly percentage impedance was given, percentage resistance was given. Okay, yes. Percentage impedance is equal to 5%. Percentage resistance is equal to 3%. Can I calculate reactance using these two? Because reactance is equal to square root of impedance square minus resistance square. Yes, impedance square is nothing but 25. Resistance square is nothing but 9. So I will get 4%. That is percentage reactance. If I know percentage resistance and reactance, I can directly find out voltage regulation at 0.8 lagging power factor, that to full load. What is the direct formula? We know percentage voltage regulation at full load. At full load, yes, the formula is percentage resistance into cos phi, which is the power factor, plus percentage reactance into sin phi, that is the value. And you are using a positive sign here because the given power factor is lagging. Suppose if the given power factor is leading, we have to use a negative sign here. Now according to the given question, resistance is 3%, power factor is 0.8 lagging, reactance is 4%, and sin phi becomes 0.6. Okay, so this is 2.4 plus 2.4, which is 4.8%, right? So the answer is 4.8%, which is option A. Easy question. Remember guys, percentage impedance drop or percentage resistance, both are same only. Per unit impedance drop or per unit impedance, both are same only. Understand? Okay, so we have one more question. This is in GATE 2019 question paper. This is also based on voltage regulation of transformer. Read the problem. A 5 kVA 50 volt by 100 volt single phase transformer has secondary terminal voltage of 95 volt when loaded. The regulation of the transformer is how much? Very simple question. See the voltage ratings of the transformer given. It is 50 by 100 volt. That means when I give 50 volt as input, I will receive 100 volt as output. Okay. But the same 100 volt is not maintained till the terminals of the transformer. Only 95 volt appeared here. This is where the load was connected. This is the resistance of the transformer, and that is the leakage reactance of the transformer. And here we have the terminal voltage, which is 95 volt only according to the given question. That means this is nothing but E2 here. This is E1. So this is the equivalent circuit of transformer, referring every parameter to secondary side. Now what is the formula for percentage voltage regulation? Percentage voltage regulation is simply equal to E2 minus V2 divided by E2 into 100. Okay, into 100. And if I substitute the data, yes, E2, that is a secondary induced EMF 100 minus terminal voltage 95 divided by 100. Therefore, the answer is 5%. Okay, simple question, straightforward question. 5% is the voltage regulation of the given transformer. Okay, there is a drop in the voltage. All right, let's move to the next problem. This is from GATE 21 question paper. A single phase transformer has a magnetizing inductance of 250 millihenries and a core loss resistance of 300 ohm referred to primary side. When excited with a 230 volt 50 Hz sinusoidal supply at the primary, the power factor of the input current drawn with the secondary on open circuited. Very easy question. Yes, see here, secondary is open circuited. That means a transformer is under no load condition. In a no load condition, transformer will draw two currents. One is loss component current IW, another one is magnetizing current I mu. So what is the formula to find out loss component current IW? Yes, formula. IW is equal to supply voltage V divided by core loss resistance RC. Okay, it is an active component shown by a resistance in shunt with a supply. What is the supply voltage given in the transformer? 230 volt divided by what is the core loss resistance? 300 ohm. So if I solve this, 230 divided by 300, Yes, I am getting 0.766 ampere. Okay, this is loss component current value. 0.766 at an angle 0 I have to write. Why? Because it is a purely active component passing through a resistor. And there is another current known as magnetizing current, which is a purely reactive component. It is shown by an inductive reactance known as magnetizing reactance. And what is the formula for magnetizing reactance? 2 pi f into L. And in the given question already L value was given. What is the inductance? 250 millihenries. So substitute everything, you will get magnetizing current. Yes, voltage is 230 divided by 2 pi into frequency 50, right? Frequency is 50, inductance is 250 millihenries. That is 250 into 10 power minus 3. This will directly tell you what is magnetizing current. So if I solve it, 2 pi into 50 into 250 into 0.001. Okay, I am getting 2.92 amperes. Magnetizing current is 2.92 amperes, but I have to write it as at an angle minus 90 degrees. Why? Because magnetizing current is a purely reactive component lagging the voltage by 90 degrees. Therefore, what will be the total no load current? Yes, but the answer that we need is that what is the power factor of the input current drawn? But for that purpose, I need to calculate the total no load current. Yes, see that. 1 second. So total no load current I naught is equal to IW plus I mu. You have to add both of them vectorially. IW, what is the value of IW we got? 0.766, 2.92. 0.766, this is at an angle 0. 2.92, this is at an angle minus 90 degrees. So if I add both of them, definitely I will get magnitude first. 0.766 whole square plus 2.92 whole square, and angle will be minus tan inverse imaginary part 2.92 divided by real part 0.766. But the requirement is angle because I wanted to find out power factor. Okay, so I don't mind about the magnitude, I need the angle. So tan inverse 2.92 divided by 0.766. Yes, I am getting minus 75.25 degrees. Okay, this is the current value. If I know angle, I can find out power factor. What is power factor? Is equal to cos of that angle. 75.25, definitely lagging power factor because there is a negative angle, right? So the final answer is cos 75.25. Yes, the answer is 0.254 lagging. If I made any mathematical errors, please correct them, but the procedure you need to understand. Okay, so the answer is 0.254 lagging. That is the correct answer. Okay. Okay, so we have the next question. This is also from GATE 21 question paper, instrumentation paper. Read the problem. A toroid made of CRGO has an inner diameter of 10 centimeter and outer diameter of 14 centimeter. The thickness of the toroid is 2 centimeter. 200 turns of copper wire is wounded on the core. Mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. And mu r of the CRGO steel is 3000. When a current of 5 milliampere flows through the winding, the flux density in the core in millitesla is how much? Okay, you need the answer in millitesla, flux density. So we know that flux density is equal to flux per unit cross-sectional area, right? What is the formula for flux? Flux is equal to mmf by reluctance. Okay, therefore this will be mmf by area into reluctance. Okay, flux is equal to mmf by reluctance. Again, what is the formula for reluctance? So mmf divided by area into reluctance is equal to length of the core by mu into cross-sectional area. Therefore, what is happening here? Area and area will get cancelled. Mu will go to the numerator. That means density is equal to mmf multiplied by mu divided by length of the core. Is it nothing but flux density finally? What is the formula for mmf again? Number of turns into current multiplied by permeability divided by length of the core. But what type of core is given here? It was clearly mentioned a toroid. A toroid means it's like a ring, okay, a circular ring. So if I draw the diagram, you can see this is how a toroid looks like. Okay, this is how a toroid looks like. And there were two diameters given if you read the problem carefully. One is inner diameter, another one is outer diameter. Okay, you see that? Inner diameter 10 centimeter, outer diameter 14 centimeter. Okay, now see that this is nothing but inner diameter. This is 10 centimeter. This is nothing but outer diameter, which is 14 centimeter. But in order to calculate the length of the core, I need mean diameter. Remember very, very carefully, the length of the core you can find out by using mean diameter. Mean diameter means you have to take it from the center to center, not from the edge to edge. You have to take from center to center. This is what the mean diameter is. Mean diameter, let's say D. So can you tell me, if outer is 14, inner is 10, what is the mean diameter? 12 centimeter. Therefore, the mean diameter of this core is 12 centimeter. If mean diameter is 12 centimeter, then what is the total length of the core? Total length of the core means I need perimeter of this circle. That's all. Because flux is passing like this, am I right? When you wound a wire on this core, flux will pass along this particular core. Therefore, length of the core means perimeter of this circle. Diameter is already there. What will be the perimeter value? Therefore, length of the core is pi into diameter. Therefore, pi into 12 centimeter, that is 10 power minus 2 meter. This is the length of the core. Once I know the length of the core, I can go back to the previous formula. I can substitute directly. Okay, B is equal to mmf into mu by length of the core. I will try to do it here itself. mmf means number of turns into current. How many number of turns were there? 200 turns. 1 second. 200 turns. Current is 5 milliampere. Relative permeability, you see, relative permeability 3000. So just directly go through this. 1 second. Yes. So here the density is equal to mmf into mu divided by length of the core. mmf is number of turns into current into mu divided by length of the core. Mu can be written as mu naught into mu r divided by length of the core. How many turns? 200 turns. Current is 5 milliampere. 5 milli means 10 power minus 3. Mu naught is always 4 pi into 10 power minus 7. Mu r given as 3000 divided by length of the core we found already, pi into 12 into 10 power minus 2. So pi into 12 into 10 power minus 2. So you can easily understand 1 pi will cancel here and solve this particular solution. You will get the answer for flux density in Tesla. Actually, you will get the answer in Tesla, then convert into millitesla. The answer finally I need in millitesla. So let me calculate. So I am getting 2.5 into 10 power minus 3 Tesla. 2.5 into 10 power minus 3 Tesla means 2.5 millitesla. This is the final answer. Okay, it's a direct question. It's actually an instrumentation paper. That's why for instrumentation students it looks difficult, but for electrical students, if you practice properly, this is an easy question. Okay, they are just asking us to find out flux density, flux per cross sectional area, flux formula mmf by reluctance, and you just substitute the data and find the answers. Okay, that's all. So these are the questions that we have in the past 13 years, 1 mark questions in transformer. Okay, so let's see how many number of questions we got. So we have around 12 questions in the past 13 years of gate question papers in transformers for 1 mark. Therefore, you can expect at least one 1 mark question from transformers subject. Okay, right. So in the next lecture, I will take up the 2 marks questions that we have in transformers as a separate video. Okay, thanks for watching. Thank you.